Assume that the car shown is not hitting the gas or brake as it rolls over this hill. We want to draw a motion map, and also we'd like to draw the vectors Fc and Ftan, which are the centripetal and tangential components of the net force. We want to do this for several different positions of the car and consider the relative forces in the force diagram. So a motion map for something like this just starts with just a picture of where the vehicle will be located at different times. All right, now I want to show the forces that are acting on the car at these different points. Now we know that the car is going to have a large weight to it. And that weight is not going to change no matter where it's located. So let's start with that. This is Fg. Okay. Our car is also on a hill. So it's in contact with a surface. This means there will be a normal force on the car. But a good question is, how big should the normal force be? Now let's recall for a moment that when we worked with ramps that were straight, there was an Fg involved. And we said that part of that force of gravity could be considered to be pulling the object into the ramp, and part of it would be pulling down the ramp. These were Fgx and Fgy. I'm going to give them different names this time, though. I'm going to call them Fg parallel and Fg perpendicular. Parallel meaning parallel with the ramp surface, perpendicular meaning perpendicular to the ramp surface. We had also said that the normal force in this situation would have to be equal and opposite to Fg perpendicular. And if we want to maintain constant speed in a situation like this, then we're going to have a force from the vehicle's engine. F, pushing the car up the hill. So some parts of this are going to be similar and some parts will be a little different here. First of all, we can find the Fg perpendicular. That's just a matter of creating a rectangle where the components are sides of that rectangle. So let's call this guy Fg perpendicular and Fg parallel. All right, now the question is, how big should the normal force be? Should the normal force from the ground be as large as Fg perpendicular, like it was in this ramp, or should it be something else? Well, one thing that we always see with centripetal motion is that it follows a formula. Fc equals mv squared over r, or in other words, Fc equals m times AC, where AC represents the centripetal acceleration, which points in toward the center of a curvature. So here, since our curvature is like a part of a circle, its center could be somewhere around here. And according to the theory of centripetal motion, in order to have a curve where your velocity vector is changing direction like this, then there has to be a centripetal force. But there's no way that there could be a centripetal force if the normal force was equal to Fg perpendicular. If we had balanced forces like this, then what would happen is the particle would travel in a straight line as it does on this ramp here. In order to make it travel in a curved path, we can't have the normal force be that big. The normal force has to be actually less than Fg perpendicular. Now there's an unbalanced force, and it's not going to change the speed of the car. It's just going to change the direction so that it follows a curved path. Now, what implications does this have for the peak? Should the normal force be as large as the Fg? Or should it be larger? Or should it be less? Well, according to the theory, what we need is we need a net force all the time on the curve. It's called the centripetal force. This is what the sum of those components N and Fg perp have to be. So the only way we can have a net force that's downward at the peak is if the normal force is not as large as Fg. All right, I'll go ahead and complete the diagram for the other positions. This is just qualitative. I don't have any numbers that go with it. Okay, and that's what I have so far for our hill. Now we want constant speed here. But does this diagram really show a car at constant speed? The answer is no, it actually doesn't. The reason why is we see an unbalanced force in the direction down the hill here. There's nothing to match it on the other side, which means that this car would be slowing down as it goes up that hill. And same thing here. I see we are at constant speed here at the peak because there's nothing in the left or right direction. But here there's an unbalanced force pulling us down the hill and then a larger unbalanced force pulling us down the hill. So this would be a car that's speeding up as it goes down the hill. So in order to maintain constant speed, yes, the driver does have to hit the gas in order to make that happen. Where do they have to hit the gas on the hill? On the way up or the way down? The answer is they have to hit it on the way up. We have to perfectly oppose the Fg parallel here with a force from the engine pushing us up the hill in order to maintain constant speed. And we have to have that here as well. So the person can actually ease off the gas as they get toward the peak. When they are at the peak, they don't want to hit the gas or brake at all. But what about on the way down? Should they hit the gas or the brake? Well, they hit the gas on the way up. And they have to hit the brake on the way down. Try the next one for yourself. See if you can draw a motion map like I did, and then reason out what the answers to the questions below would be. All right, so I'll start with my motion map. Our weight of the car always pulls down. Let's break that weight down into its components. A perpendicular component and a parallel component. Okay, now the question becomes, how big should the normal force be? And the centripetal force always has to point in toward the center of curvature. It is the thing that causes the path of the particle to bend. So in this particular valley type situation, our centripetal force will be directed inward toward the center of this half circle. Since the centripetal force is actually a component of the net force, we need a net force that points in toward the center of curvature. So should the normal force at the bottom of this valley be larger than Fg, or the same size as Fg, or smaller than Fg? And you might think about what it's like to ride a roller coaster in these situations. So like if you're on a roller coaster where you come into a valley, do you feel heavier or lighter? The answer is you should feel heavy because there's a normal force being applied underneath you that's larger than your own weight. So the normal force needs to be big here. These vectors, when added together, equal that centripetal force pulling the object toward center. Okay, so in each case, our normal force needs to be bigger than it would have been on a straight ramp. Okay, now if we're going to go through this valley at constant speed, where do we have to hit the gas and where do we have to hit the brake? Well, Fg parallel would be an unbalanced force in this diagram. We have to counteract it with a force in the opposite direction. And would this come from the gas or the brake? That would be the force of the brake. So you'd brake on the way down. Then you want to neither hit the gas nor brake here. Then we want to hit the gas on the way up. Then we can maintain constant speed.